Okay, iterated limits are one of the biggest no-nos in Calc 2. Okay, so before I say anything else, I'm going to write big no-no. You do not want to touch iterated limits ever in this course or ever. Okay, it's confusing and it just doesn't do what you want it to do. However, it's very tempting. Even if I hadn't, so you might ask, why do I even tell you about them? Because if I wouldn't tell you about them, you would invent them by yourselves, okay, and then get into a lot of trouble. So what are iterated limits? Iterated limits are things of the form limit, so we have f of xy, and we defined it in a very certain way, right? But you can ask, what if we take f of xy, freeze y, regard y as a parameter, take the limit as x goes to 0. Not to 0, sorry, to a, to some point a. Whatever we get is not going to have x's in it any longer. It's going to be that limit that we found, but it still has y as a parameter in it. Now take the limit as y goes to b. This is called an iterated limit. It's taking a one variable limit and then another one variable limit. Okay? And why is it such a big no-no? Why do we never want to do this? Because this is not the same thing as the limit which we defined and calculated, and which is the right thing to do and the thing that works for everything we're going to do later, for derivatives and for continuity and for everything. Okay? This just gives you something which is, I can't say unrelated. I'm going to write a short theorem that does relate them in a certain sense, but in general, this expression, this, does not imply anything about the limit of fxy as xy goes to ab, the limit we've been discussing for the past 1 or 2 or 3 hours, I don't remember. Okay? And of course there's the other one. You could first freeze x and then freeze y, and both of them, and what do I mean by does not imply anything? Okay? So this can exist and be finite, whereas this doesn't. Vice versa. This can exist and this cannot exist. Okay? And the only statement that really, the only theorem regarding this, and I'm going to state it, but you can see that it doesn't tell you too much, is if the limit exists. So you have to know that the limit exists, and if you already know that, why would you want to use those? So if this limit exists, and one of the iterated limits exists, there are 2 of them, depending on which variable you take to the limit first. Iterated limits exists, then they are equal. Okay? And if all 3 exist, then all 3 are equal. Okay? But clearly this doesn't help you calculate this, because to know that they're equal, you have to know that this one actually exists. You have to find it first. Okay? So that's the only statement. So let's write, but lim xy goes to ab of fxy can exist without or let's write let's write that but one can exist without the other. Okay? And this is not some phenomenon that happens in very remote, weird, pathological functions. We've actually seen examples. So we've only calculated limits of like 3 examples, right? And they exhibited most of these situations because it just always happens. So example 1, we discussed the function fxy equals x sine 1 over y plus y sine 1 over x and 0. Remember this function? We calculated this using one of the definitions of the limit, and we found that the limit of this function as x approaches 0 is 0. Okay? So here the limit does exist. We proved it by definition, but the iterated limits don't exist. What do I mean don't exist? Freeze x. Try taking y to 0. Okay, we're talking about the point 0, 0. Freeze x, try taking y to 0, but sine of 1 over y doesn't have a limit, right? You know that, right? So the iterated limits doesn't exist. Freeze y, try taking x to 0. Well, this will go to 0, but this doesn't exist. Do you agree? Sine of 1 over x doesn't have a limit as x goes to 0. Right? You know that function. It's the accordion sort of thing. Right? Everybody knows what I'm talking about? So here, in this example, the limit, we just proved it. The limit f of xy equals 0 as xy goes to 0, 0. But both iterated limits don't exist. Clear? Okay, so if any consideration of the iterated limit, you would try to from it deduce anything about the limit itself, you'd get a wrong answer. Okay, the limit does exist. Clear? And on the other hand, here's another example. If you look at another example we talked about, fxy equals xy over x squared plus y squared and 0. Okay, this was the example where along different lines approaching the origin, we got different limits, m over 1 plus m squared. Remember that? Okay, so we discussed this example. So here we showed that the limit doesn't exist. We showed that the limit as xy goes to 0 of fxy doesn't exist. Okay, along different straight paths approaching the origin. However, what about the iterated limits? So suppose we freeze x and let y go to 0. Freeze x is some fixed number now. Let y goes to 0. So the denominator goes to x squared, and the numerator goes to 0. So the whole thing goes to 0. So if you fix x, let y go to 0, we get 0, and then we let x goes to 0. It's still 0 because there's no x's left, and vice versa for y. So both iterated limits exist and are 0. Do you agree? Okay. So doesn't exist, but both iterated limits are 0. Clear? So conclusion, don't be tempted. Okay? Don't be tempted, even if you're looking at it and I can take x to 0, see what happens. It just doesn't say anything about the limit. Okay? And the surprising thing about this is only going to be revealed later on in the semester when we talk about integrals, and we're going to see that iterated integrals play a crucial role in this course, are very important. But just for limits, just don't touch them. Never. Questions? Yes?
When would we use this theorem?
the question is, when would we use this theorem? Since what I recommended is don't touch iterated limits, in particular, you won't use this theorem. Okay? I'm just saying, I just wrote it down to say that it's not a non-theory. It's not that we can't say anything about them. So in the very special case, when an iterated limit and a limit exist, then they're equal. Okay? So if for some reason, I can make up a question if I'm really evil and say, suppose you know that this limit exists and calculate it using an iterated limit. Okay, so then if you calculate, you see the iterated limit exists, and I just told you that this limit does, then you know it's equal. But that's usually not a standard form of a question. How would you know a limit exists unless you calculate it or find it or use some reasoning to... Okay, bless you. More questions? Okay, so that's this discussion. If you think for a minute what an iterated limit does, freezing x, here's the origin. Okay, I'm thinking of the origin. It's of course defined for any a, b, but here's the origin. Okay, 0, 0. Freeze x, I'm freezing x, taking the limit as y goes to 0, and then taking x to 0. Do you see that? I'm choosing a very, very specific path along which I approach the origin. You can see why it has nothing to do with the existence of the limit in general. Okay? Because I'm just choosing a very specific path, or a very specific path the other way. Okay? If the limit exists and all the iterated limits exist, then they have to be equal. Okay, that's this theorem. Okay, clear? Okay, so that's about iterated limits, and we're not going to mention them again in this course. Okay.